Welcome back to The Explainer. Today we're diving into a genuinely fascinating piece of database architecture, multi-leader replication. If you've ever wondered how the world's biggest apps manage to keep data synced across the globe without making you sit there staring at a loading screen, well, you're in exactly the right place.
All right, to kick things off, let's picture a scenario. Imagine you've just built this incredibly successful application. It goes viral, and suddenly you've got millions of active users spread across Tokyo, London, New York, and Sydney. But here's the catch. Your database leader, that single server responsible for accepting all new data updates, is sitting in a solitary data center in San Francisco. So, what happens when a user in Sydney tries to save a post? They get hit with massive network latency because their data has to travel all the way across the ocean and back. It becomes an absolute bottleneck.
Okay, let's dive into this. Today, we're going to cover this single-leader bottleneck, how multi-leader replication steps in to fix it, a few real-world use cases, the inevitable right conflict problem, how we actually resolve those conflicts, and finally, the ultimate trade-off.
Part 1. The single-leader bottleneck, or what happens when one node just isn't enough. So, in a standard database setup, we usually rely on single-leader replication. What that means is every single time data changes, whether it's an insert, an update, or delete, it absolutely must pass through one central primary node. That primary node processes the change and then copies the data out to its followers. Now, having this central bottleneck is great for guaranteeing order, which keeps things simple and consistent. But as we just imagined with our San Francisco data center, it completely breaks down when your users are geographically far away, or worse, completely offline.
Moving on to Part 2. Enter multi-leader replication, scaling the writes.
Multi-leader replication, which you'll also hear called active-active replication, is this clever architectural setup where multiple independent database nodes are given the authority to simultaneously accept write requests. In this setup, every single leader node actually doubles as a follower to all the other leaders. So, when one leader receives a write from a user, it processes it locally first, and then it immediately streams that data change over to the other leaders to keep the whole global system synced up.
And this brilliantly illustrates how it actually plays out across two separate data centers. Let's say data center 1 is in New York and data center 2 is in London. Each one has its very own leader. A user in New York sends their read and write queries to their local New York leader, while a user in London sends theirs to London. The magic happens in the background. The leaders asynchronously sync with each other across the ocean. By placing a leader in each region, we completely hide that cross-world internet latency from the end user. To them, their writes happen instantly.
All right, Part 3, real-world use cases. Let's look beyond the data center.
Think about a calendar or a collaborative notes app on your smartphone. You expect to be able to add a meeting or jot down a grocery list even if you're stuck on a subway with zero internet connection, right? Well, when you do that, your phone is essentially acting as a local database leader. It accepts the write locally and immediately while you're offline. Then, when you finally step off the subway and get your connection back, a background process kicks in and syncs your local phone leader with the main server, which is just another leader. It is the exact same multi-leader principle, just taken to the extreme where your mobile device is basically acting as a highly unreliable, disconnected data center.
Which brings us to Part 4, the write conflict problem. Here is the plot twist.
Allowing data to be changed in multiple places at the exact same time creates a massive complication. We call this the problem of concurrent modifications. See, if you only have one leader, it gets to decide the absolute order of events. First this happens, then that happens. It's clean. But when two independent leaders are accepting updates simultaneously, the whole concept of what happened first completely breaks down, and things get incredibly messy. Now, what's really interesting here is how a conflict actually plays out in action. Let's say we have a wiki page with the title A. User 1 connects to their local leader and changes the title to B. But at the exact same time, user 2 connects to a different leader and changes the title to C. Both leaders happily accept the write and tell their respective users, awesome, saved. But later, when those leaders try to asynchronously replicate to each other in the background, the first leader says, hey, change A to B, while the second says, wait, I already changed it to C. They hit a massive wall.
To break that down super simply, we have two completely valid, simultaneous updates. User 1 wants the title to be B, and user 2 wants it to be C. So which one is right? In a multi-leader system, neither order is intrinsically more correct than the other. If our system doesn't handle this properly, the first leader might end up with title C, the second might end up with title B, and boom, our database is permanently inconsistent.
So how do we fix it? Part 5, resolving write conflicts, engineering the fix.
System designers basically have a few main strategies to wrangle these conflicting databases back into a consistent, uniform state. The easiest is conflict avoidance, just making sure all edits for a specific record always route to the exact same data center. But if you can't avoid conflicts, you have to resolve them. Some common strategies include last write wins, merging the values together, or leaning on custom application logic.
Let's zoom in on last write wins, or LWW. It's incredibly popular. In this method, the system just attaches a timestamp to every write, and when a conflict happens, it simply picks the write with the latest timestamp as the winner and throws the other one away. Sounds super simple, right? But I have to heavily caveat this. It acts as a dangerous shortcut. Since it literally discards the older concurrent write, it causes intentional data loss. If losing user data is unacceptable for your app, last write wins is a terrible choice.
And network delays make this an even weirder problem. Imagine client A inserts new data into the first leader, while client B updates that exact same data on a third leader. But because of network congestion, a second leader right in the middle might actually receive the update from client B before the initial insert from client A even arrives. It's being asked to update a record that doesn't exist yet. This causality problem proves why simply slapping a timestamp on an event isn't always enough, especially since system clocks across different servers are almost never perfectly synchronized.
Because of these wild edge cases, the safest choice for an engineer is often just writing custom application code that gracefully handles conflicts. You might do this on the read side, so you store all the conflicting versions, and then the next time the data is read, you prompt the user to manually fix it. Or, alternatively, you can use specialized data structures to merge changes automatically in the background. Think about collaborative editors like Google Docs. They take everyone's simultaneous typing and cleverly merge it all together so nobody's work gets lost.
Finally, Part 6, the ultimate trade-off, availability versus correctness. So the crucial point to take away from all this is, we implement multi-leader replication because we desperately want global availability, lightning-fast writes, and seamless offline support for our users. But the unavoidable toll we pay for those amazing benefits is write conflicts and complex resolution logic. Ensuring your data is completely correct becomes significantly harder when you decentralize authority. You're intentionally trading the simplicity of a single timeline for the speed and resilience of multiple, concurrent timelines.
Which leaves us with a critical question to ponder. When you're mapping out your next system design, and you're looking at your user base and your business requirements, are you willing to trade absolute data correctness for global availability? It's a compromise you'll inevitably have to navigate. Thanks so much for joining me today on The Explainer as we unpacked multi-leader replication. Keep questioning how your data flows, and I'll catch you in the next one.